October 1st, 2025, the European Space Agency announces publicly that Mars Express and the Trace Gas Orbiter will observe 3I Atlas during its closest pass to Mars. Not a rumour, not a leak. An official statement. NASA's Mars Reconnaissance Orbiter, the UAE's Hope Probe, and China's Tianwen-1 are all positioned with eyes on the same target. 5 spacecraft, billions of dollars in hardware, the perfect cosmic alignment for humanity's best look at an object from beyond our solar system. Then something bizarre happens. Silence. No images, no press releases, no data drops. Just one blurry stack of 20 rover frames circulating on social media, processed by an astrophotographer named Simeon Schmaus, and later calibrated properly and shared on X by popular cosmologist Stephen Burns. That single smudge becomes the only visual evidence the public gets to see. Meanwhile, China, a country that floods the internet with thousands of Mars images, that celebrates every space achievement as proof of superiority, says nothing. Not a word, not a pixel. For a nation obsessed with showing the world what it can do, that silence is deafening, and it gets stranger. WST spectroscopy shows something no one expected. Nickel without iron, a chemistry profile some scientists are calling orders of magnitude more consistent with industrial origin than natural formation. This is a 3-act exploration. Act 1 covers the viral discovery and the information blackout. Act 2 explores the scientific and political implications, and Act 3 dives into other breaking space news that have been drowned out in the 3I Atlas noise. Before we go deeper, if this story grabs you, hit that like button and subscribe. Tell me in the comments, where are you watching from? What's your take on the silence? And do you think we're looking at a comet or something else? Also, if you want to help spread the word, share this on X, Reddit, or wherever your community gathers. Thank you for being here. Let's find out what they're not telling us. Part 1. The tweet that started it all. The screen lights up at 3 in the morning and suddenly everyone is awake. A single post appears on X, formerly Twitter, from an account called 3I Atlas _anomaly. The words are simple, almost casual. The silence from China is deafening. Within minutes, the metrics explode. The internet, that great collective nervous system, has just felt something strange pulse through its wires. To really understand why this matters so much, let's backtrack a bit. On October 3rd, 2025, 3I Atlas made its closest approach to the Red Planet, passing within approximately 29 million kilometres, or 18 million miles. That might sound distant, but in astronomical terms, it is a front-row seat. Multiple space agencies announced their intention to observe this rare event. The European Space Agency positioned Mars Express and the Trace Gas Orbiter for observations. NASA's fleet of Mars spacecraft and rovers stood ready. The United Arab Emirates Hope Orbiter adjusted its instruments. China's Tianwen-1 mission, which had been photographing the Martian surface for years, was perfectly positioned to capture unprecedented images of an interstellar object from another world. The anticipation was electric. Imagine it. Humanity's robotic emissaries, scattered across Mars' orbit and surface, all turning their cameras toward the same patch of sky. We would see an interstellar visitor from a vantage point 33.5 million miles from Earth. We would triangulate, measure, compare. The data would be extraordinary. Except the data never came, or rather it did not arrive in the way anyone expected. Instead of crisp orbital images, instead of press releases and data dumps and scientific papers uploaded to preprint servers, the world got something else entirely. A smudge. A controversial, blurry, elongated smudge extracted from the raw image files of NASA's Perseverance rover, processed by citizen scientists, amplified across social media, and debated in every corner of the internet that cares about what might be watching us from the dark. That tweet, simple and devastating, captured the paradox perfectly. For a country obsessed with broadcasting its technological prowess, for a space program that regularly publishes thousands of images, for a geopolitical superpower that treats Mars exploration as a stage for demonstrating superiority, the silence is not just unusual, it is deafening. But China is not alone in its quiet. NASA has released no close approach images from its Mars orbiters. The European Space Agency, which publicly announced observation plans for October 1st through 7th, has posted nothing from that critical window. The UAE's HOPE mission, typically eager to share data from the first Arab interplanetary spacecraft, remains silent. Every major player, every camera, every instrument that should have been watching, appears to have collectively decided that this moment, this unprecedented celestial event, is not worth sharing with the public. What normally happens when space agencies capture something interesting? The process is well established, almost mundane in its predictability. Raw images get downloaded from spacecraft, often within hours or days. They appear on public servers, sometimes still embedded with calibration artifacts, hot pixels, cosmic ray strikes. Scientists begin preliminary analysis while the data is still warm. Press officers draft statements. Researchers prepare papers. The machinery of public science, transparent and iterative, grinds forward. Delays happen, certainly. Bandwidth constraints, instrument anomalies, calibration backlogs, staffing limitations, all these can push timelines from days to weeks. But a total absence, across multiple agencies, multiple spacecraft, multiple nations, that pattern does not fit any routine explanation. The internet, nature abhors a vacuum, and the internet abhors an information vacuum even more. Two narratives split almost immediately. The first camp, measured and cautious, invokes routine pipeline delays, pointing complexities, signal-to-noise ratio concerns. These are professionals and enthusiasts who understand how space missions work, who know that not every observation yields publishable results, who remember past instances where expected data took months to appear, if it appeared at all. The second camp sees coordination, sees suppression, sees something significant enough to warrant unprecedented interagency silence. These are the people who ask uncomfortable questions. Why would every single spacecraft with a view of 3i Atlas simultaneously experience data issues? Why would agencies that typically compete for prestige suddenly align in their collective reticence? The question hanging over everything, unspoken but impossible to ignore, is this. If 3i Atlas were just a normal comet, some dirty snowball from another star system following physics and chemistry we already understand, why would any government choose silence over celebration? Why would Beijing, which has spent decades building a reputation as a spacefaring superpower, pass up an opportunity to publish first, to claim the best images, to flex its technological muscle in front of a watching world? The silence, as the tweet says, is deafening, and what makes silence truly frightening is not what it hides, but what it suggests about those who choose it. Part 2. The cylinder in the Martian sky. The image appears unremarkable at first glance, just another grainy frame from a rover camera looking up at an alien sky. Then someone adjusts the contrast and suddenly you see it. An elongated shape, glowing faintly, stretching across the Martian atmosphere like a luminous scratch on old film. The caption on the post from TruthPollX reads, "Does this look like a comet to you?" Another user, for all curious, shares a cropped and colour-enhanced version, the object now tinted green, its edges seemingly crisp, its proportions suggesting something cylindrical, something with uniform internal brightness. The comments explode with speculation. Metallic, structured, impossible. This is the image that broke containment, the single piece of visual evidence that escaped the apparent data blackout and spread across the internet faster than any official correction could follow. It comes from NASA's Perseverance rover, specifically from the Mastcam Z instrument, a stereoscopic camera system designed to photograph rocks and soil samples, not fast-moving objects in the sky. The raw image files, as they always do, appeared on NASA's public servers. What happened next was citizen science at its most aggressive. A German data analyst named Simeon Schmaus downloaded multiple frames, aligned them to compensate for the rover's slight movements, stacked them to reduce noise, and applied contrast enhancements to pull faint signals out of the background. The result was the elongated glow that now dominates every discussion of 3i Atlas. Astrophysicist Avi Loeb, director of Harvard's Galileo project, and perhaps the most prominent voice arguing for serious scientific investigation of potential interstellar artifacts, referenced this stacked image in a Medium blog post, describing it as a smudge, but acknowledging its existence in the data. So what are we actually looking at? The mundane explanation is straightforward, almost disappointingly so. When a camera captures a moving point source across multiple frames, especially when those frames are later aligned and combined. The motion itself creates elongation. Imagine photographing a distant airplane at night with a long exposure. The plane's lights streak across the frame, creating the illusion of a glowing rod rather than a point. The Mascom-Z system was never designed for tracking fast celestial objects. Its exposure settings, its frame rate, its alignment algorithms, all optimized for stationary geology, conspire to smear anything moving across the field of view. Add to that the digital processing applied after the fact. Stacking introduces artifacts. Contrast enhancement amplifies noise. Hot pixels, those individual detector elements that malfunction and report false brightness, can create spurious signals that look like structure when stretched and filtered. The green tint that appears in some versions is almost certainly a false colour map, applied to make faint features more visible, not the actual colour of the object. Anyone who has worked with astronomical images knows that what you see after processing may bear only a passing resemblance to what the instrument actually recorded. And yet, the image persists. The cylinder interpretation persists. Because this grainy, contested, possibly artifact-laden smudge is the only visual evidence the public has from the Mars observation window, not because better images do not exist, but because better images have not been released. The orbital spacecraft, with their higher resolution cameras, their precise pointing systems, their ability to track moving objects, should have captured definitive data. Mars Reconnaissance Orbiter carries HiRISE, a camera capable of resolving features less than a metre across on the Martian surface. Mars Express and the Trace Gas Orbiter have instruments designed for atmospheric science and surface mapping. Any of these platforms properly tasked could have delivered images that would settle the question instantly. Instead, we have a smudge. And the human mind, that pattern-seeking engine honed by millions of years of evolution to spot predators in tall grass and faces in clouds, looks at the smudge and sees structure, sees symmetry, sees intent. Compare this to the Hubble image from July. That picture, released through proper channels with calibration notes and scientific context, shows a classic cometary appearance. A bright nucleus surrounded by a fuzzy coma, the cloud of gas and dust liberated as ice sublimates in sunlight. The shape is teardrop-like, slightly asymmetric, exactly what you would expect from a dirty snowball warmed by solar radiation. It looks natural. It looks safe. The Perseverance smudge looks like neither of those things. Whether that difference reflects reality or merely reflects the limitations of an instrument used beyond its design, specifications remains an open question. But the psychological impact is undeniable. Mainstream outlets picked up the story. Science journalists wrote explainer pieces, most of them cautious, many of them skeptical, but all of them acknowledging that something unusual was happening in the information ecosystem around 3i Atlas. Alternative science platforms, less constrained by institutional caution, ran with more provocative headlines. The Debrief, a publication that focuses on unexplained phenomena and aerospace technology, covered the image and the subsequent silence extensively. The virus had escaped the lab. The cylinder in the Martian sky became a meme, a shorthand, a cultural touchstone. People who could not tell you the difference between an asteroid and a comet now had an opinion about 3i Atlas. The image circulated on platforms that never discuss astronomy. Influencers who built careers on entirely unrelated topics suddenly posted about interstellar visitors and government secrecy. And through it all, the space agencies said nothing. No correction, no clarification, no alternative explanation. Just silence, while the smudge did their talking for them. What happens when the only evidence available to the public is the worst evidence? Processed by amateurs, filtered through social media, untethered from institutional credibility. You get exactly what we're seeing now. A story that writes itself, a narrative that fills the vacuum left by official reticence, a collective fever dream, powered by pixels and paranoia. The cylinder may be an illusion, a trick of light and software, a cautionary tale about the dangers of overinterpreting noisy data. But the silence surrounding it is absolutely real, and that silence, more than any image, is what keeps people awake at night, scrolling through contrast-enhanced crops, asking the same question over and over: does this look like a comet to you? Part 3. 4 eyes, 1 smudge. 5 platforms orbited Mars on October 3, 2025, each carrying instruments worth hundreds of millions of dollars, each positioned to observe an interstellar visitor from a perspective humanity had never achieved before. NASA's Mars Reconnaissance Orbiter, launched in 2006, circles the red planet every 2 hours, carrying the high-rise camera system capable of resolving objects the size of a dinner table from orbit. The European Space Agency operates 2 spacecraft, Mars Express, in orbit since 2003, equipped with a high-resolution stereo camera and spectrometers, and the Trace Gas Orbiter, which arrived in 2016, with instruments designed to sniff atmospheric composition and photograph surface features in exquisite detail. The United Arab Emirates Hope Orbiter, the first Arab interplanetary mission, reached Mars in 2021, carrying cameras and spectrometers optimized for studying the Martian atmosphere and weather patterns. And China's Tianwen-1, which entered orbit in 2021 and deployed a rover to the surface shortly after, carries both orbital and ground-based instruments capable of imaging and spectroscopy. 5 platforms, dozens of cameras, hundreds of scientists and engineers monitoring telemetry, planning observations, downloading data. The observation window for 3i Atlas was publicly announced. The European Space Agency explicitly stated that Mars Express and the Trace Gas Orbiter would observe the object between October 1st and October 7th. This was not a secret operation. This was open science, the kind of coordinated international observation that represents the best of what humanity can achieve when we set aside our differences and point our instruments at the same patch of sky. The closest approach occurred on October 3rd. 3i Atlas passed Mars at approximately 29 million kilometers, close enough that even modest instruments should have been able to capture detailed images of the coma structure, measure the rotation rate if one existed, analyze the spectrum of sunlight reflected and emitted by the object. The data download process for Mars missions is well established. Most orbital spacecraft have multiple communication windows with Earth each day. High-priority observations often get priority downlink slots. Raw images typically appear on public servers within hours to days, long before any scientific analysis is complete, because transparency is not just good public relations, it is mission policy, encoded in funding agreements with taxpayers. So where are the images? At the time of this recording, no official close-approach photographs from any Mars orbiter have been released. The public record consists entirely of the community-processed Perseverance rover frames, those controversial stacked images that spark the cylinder debate. The orbital platforms, the ones that should have delivered definitive data, remain silent. Let us be fair and thorough about the possible mundane explanations, because jumping to conspiracy without considering alternatives is intellectually lazy. Spacecraft operations are complex. Pointing a camera at a fast-moving object requires precise attitude control and timing. 3i Atlas was not stationary. It was streaking through the field of view at kilometers per second relative to Mars. Perhaps the pointing algorithms failed. Perhaps the observations were attempted, but the object appeared too faint or too smeared to be useful. Perhaps scattered sunlight from Mars itself contaminated the images, rendering them scientifically worthless. Perhaps the data was corrupted during transmission, garbled by cosmic rays or equipment glitches. These things happen, space is hard, instruments fail, data gets lost. The engineering margin between success and failure is often razor-thin, and even the best missions experience occasional setbacks. Perhaps every single spacecraft, through some confluence of bad luck and technical difficulty, simply failed to capture usable images. Unlikely, but not impossible. Then there is the calibration and quality assurance bottleneck. Raw images often require extensive processing before they are suitable for publication. Bad pixels need to be masked. Geometric distortions need to be corrected. Exposure levels need to be normalized. This work takes time and skilled personnel. Perhaps the images exist but are stuck in a processing queue, waiting for an overworked data analyst to validate them before release. Perhaps there are political or institutional review processes slowing things down, not because the images show anything extraordinary, but simply because bureaucracies move slowly, and multiple agencies means multiple approval chains. These explanations are plausible. They are the kind of boring, frustrating realities that characterize much of space exploration. No drama, no conspiracy, just the grinding friction of large organizations trying to coordinate across borders and time zones and competing priorities. And yet, the paradox remains. Billions of dollars of hardware, Years of mission planning, explicit public announcements of observation intent, and the only image shaping public opinion is a blurry smudge from a rover camera never designed for this task. The information asymmetry is staggering. Somewhere, on hard drives and data servers scattered across the United States, Europe, the UAE and China, the real images almost certainly exist. They were captured, downloaded, stored. Scientists have seen them. Mission planners have reviewed them. But the public, the taxpayers who funded these missions, the civilization whose curiosity propelled these machines across interplanetary space, gets nothing. The smudge seen around the world became a joke, a meme, a symbol of institutional failure or institutional secrecy, depending on your perspective. Social media metrics tell the story. The processed Perseverance images generated millions of impressions, thousands of shares, countless comment threads debating what they showed. Official space agency accounts, usually prolific posters of Mars imagery, went conspicuously quiet during the observation window. No teasers, no progress updates, no stay tuned for more. Just an eerie absence where communication normally flows. Is this normal? Can a multi-agency observation campaign simply vanish into a data pipeline for weeks or months with no public acknowledgement? The answer depends on who you ask. Veterans of past missions will tell you that delays are routine, that patience is required, that good science takes time. But even they admit that the coordination of silence across agencies that normally compete for headlines is unusual. The optics are terrible. The vacuum invites speculation, and once speculation takes root in the fertile soil of the internet, it grows faster than any correction can prune it back. We are left with a simple, uncomfortable fact. The most expensive surveillance network ever positioned around another planet observed an interstellar visitor, and the public record consists of one contested image, processed by a citizen scientist from rover data, while the agencies that promised observations remain silent. Whether that silence reflects mundane bureaucratic inertia or something more deliberate, we cannot yet say. But the question lingers, unanswered and increasingly urgent. What did those four eyes actually see? And why are we looking at one smudge instead of 100 crisp images? Part 4. China's deafening blackout. For a country obsessed with showing superiority, China's silence may be the loudest clue of all. The China National Space Administration does not do modesty. Since Tianwen-1 entered Mars orbit in February of 2021, the mission has been a propaganda masterpiece, a carefully orchestrated demonstration of technological prowess designed to signal that China has arrived as a spacefaring superpower. The data releases follow a predictable rhythm. Batches of images showcasing the orbiter's capabilities, surface photographs from the Zhurong rover exploring Utopia Planitia, press conferences timed to maximize domestic and international media coverage. Thousands of images have been published since the mission began. Panoramas of rust-coloured dunes, close-ups of rocks that might have formed in ancient water, orbital maps of polar ice deposits. Each release is accompanied by statements emphasizing Chinese innovation, Chinese engineering, Chinese scientific leadership. This is not criticism. This is observation. Every space agency engages in public relations. NASA plasters its logo on every image. The European Space Agency produces slick videos celebrating Rosetta's comet landing, or Mars Express's longevity. The space race never ended. It just became more about prestige than weapons. And in that race, China has been sprinting, eager to match and exceed the accomplishments of established players, determined to prove that authoritarian technocracy can compete with and surpass democratic science. So when 3i Atlas made its closest approach to Mars, when Tianwen-1 had a front-row seat to an event that would dominate science headlines worldwide, when Beijing had an opportunity to publish the first and best images of an interstellar object seen from another world, what did the China National Space Administration do? Nothing. Publicly, at least, nothing at all. No press release announcing successful observations, no preview images released to state media, no scientific papers uploaded to Chinese preprint servers, no social media posts from official accounts celebrating this historic moment. The usual propaganda machinery, so reliable and so loud, went completely silent. As of this recording, no China National Space Administration publication specifically showcasing 3i Atlas imagery from the Mars observation window has appeared in any public forum. Now, to be scrupulously fair, the China National Space Administration often batches its releases, sometimes holding data for weeks or months before publishing comprehensive image sets. The absence of immediate images does not necessarily indicate a cover-up. It might simply reflect institutional practice. Perhaps the data is being carefully analysed. Perhaps scientists are preparing a major paper. Perhaps the timing of release is being coordinated with domestic political events or international conferences. These are all plausible, boring explanations. But context matters, and the context here is striking. The European Space Agency publicly announced its observation plans for Mars Express and the Trace Gas Orbiter. NASA's Mars program is transparent about targeting opportunities. Both agencies typically release at least preliminary data relatively quickly, even if full scientific analysis takes longer. The symmetry of silence, the fact that every major player appears to have collectively decided not to share images from this specific event, is what alarms commentators and fuels speculation. Geopolitically, the silence is a missed opportunity that borders on inexplicable. China's space program exists not just to do science, but to demonstrate that China can do science as well as or better than anyone else. Mars missions are expensive, politically risky, and technically challenging. The return on investment is not just scientific knowledge, it is national prestige. When India's Mars orbiter mission succeeded on its first attempt in 2014, beating China to the red planet, the loss of face was palpable in Chinese media coverage. The country that had put astronauts in space, that had landed on the far side of the moon, had been beaten to Mars by a smaller neighbour with a fraction of the budget. Tianwen-1 was the answer to that humiliation. A comprehensive mission with an orbiter, a lander, and a rover, all succeeding on the first attempt, a feat no other nation had achieved. The message was clear. China has caught up, and China is pulling ahead. Every subsequent data release reinforced that message. Look what we can do, look where we can go, look how advanced our technology has become. So why, when presented with an opportunity to capture the most extraordinary images in the history of their Mars program, would Beijing choose silence? Why would they allow NASA and the European Space Agency to control the narrative by default, even if that narrative is currently dominated by amateur processed rover images rather than official releases? Why would they pass up a chance to one-up the Americans, to publish first, to claim scientific priority, to bask in global attention? The cultural and media angle adds another layer. Information flow in China is tightly controlled. Weibo, the dominant social media platform, is moderated aggressively. Posts about sensitive topics disappear. Trending hashtags get suppressed. If there were an official or semi-official release of 3i Atlas images that subsequently vanished from Chinese platforms, it would fit established patterns of information control. We have seen this before with everything from natural disasters to political scandals to embarrassing technological failures. The absence of evidence in a controlled information environment does not prove evidence of absence, but it does suggest that if something interesting appeared and then disappeared, we might never know. The speculation, and it must be labelled as speculation because we have no direct evidence, is that something in the Tianwen-1 data made Beijing hesitate. Perhaps the images were too ambiguous, too provocative, too likely to fuel exactly the kind of uncontrolled public speculation that authoritarian governments despise. Perhaps there was a request, formal or informal, from other space agencies or from defence and intelligence communities to hold off on publication pending further analysis. Perhaps the decision to remain silent was coordinated, part of a larger interagency agreement that crosses geopolitical boundaries because some discoveries are too significant for unilateral disclosure. Or perhaps, and this is the boring explanation that might actually be correct, the data was simply not very good. Perhaps the pointing was off. The images were blurry, the signal-to-noise ratio was poor, and Beijing made a pragmatic decision not to publish substandard data that would invite mockery rather than admiration. In the calculus of propaganda, a missed opportunity is better than a public failure. We do not know. We cannot know, not without access to the actual data or direct statements from the China National Space Administration explaining their silence. What we can observe is the silence itself, the fact that it exists, the fact that it is consistent with silence from other agencies, and the fact that it represents a dramatic departure from established patterns of behaviour. When a government that normally shouts chooses to whisper, when a space program that craves attention suddenly seeks none, the absence of sound becomes a sound of its own. And that sound, as the original tweet observed, is deafening. Part 5. Behind closed doors. China's silence is the sign that something's happening behind closed doors. The words appear on a screen, posted by a user called Orwelliano90, and they capture the mood perfectly. Two competing hypotheses face each other across the digital divide, each coherent, each supported by partial evidence, each demanding that we take sides. The first hypothesis is mundane and frustrating. Data pipeline delays, noisy observations, nothing scientifically exciting enough to rush into publication. Agencies doing what agencies always do, moving slowly, checking thoroughly, avoiding premature claims. The second hypothesis is extraordinary and terrifying. The data shows anomalies, structures, behaviours inconsistent with natural objects, and a temporary embargo has been imposed while governments and scientific institutions figure out what to say and how to say it without causing panic. Let us examine both with the seriousness they deserve. The mundane explanation rests on decades of space mission experience. Spacecraft operations are complicated. Data collection is only the first step in a long process that includes transmission, validation, calibration, analysis, peer review, and publication. Even high-priority observations can take weeks or months to work through this pipeline. Scientists are cautious by training and by necessity. Publishing incorrect results damages careers and institutions. Better to take extra time, to triple-check, to build consensus, than to rush into print with claims that later prove embarrassing. Furthermore, not every observation succeeds. Instruments fail. Pointing errors occur. Background noise swamps faint signals. Perhaps 3i Atlas simply did not cooperate as an observing target. Perhaps it was dimmer than expected, or its coma was more diffuse, or scattered sunlight from Mars made clean imaging impossible. Perhaps multiple agencies independently concluded that their data was not worth releasing, because it added nothing to what Hubble had already captured in July. These are unglamorous but entirely plausible scenarios. The extraordinary explanation, by contrast, requires us to believe in coordination across geopolitical rivals, in information embargoes spanning multiple countries and space agencies, in decisions made at levels above the scientific community. It requires us to imagine defence and intelligence services taking an interest, national security implications being weighed, conversations happening in secured rooms where scientists brief officials on observations that do not fit comfortable categories. How would such an embargo even work? Space agencies are civilian organisations, at least nominally, but they operate under government authority and depend on government funding. If a three-letter agency or its equivalent in other countries requested a pause in data publication pending analysis, if the request came with sufficient justification and sufficient authority, compliance might be framed as voluntary cooperation rather than censorship. The scientists would not be gagged. They would simply be asked to wait, to give the experts time to assess, to avoid triggering public alarm over data that might have innocent explanations. Historical analogues exist, though none are perfect parallels. The Rosetta mission to Comet 67, P. Churyumov-Gerasimenko encountered unexpected features that took time to explain. Some data releases were delayed while scientists argued over interpretation. Government shutdowns in the United States have paused NASA communications, creating temporary blackouts in public data flow that had nothing to do with the content of the data itself. The culture of secrecy around certain space technologies, particularly those with potential military applications, is well documented. Satellite imagery capabilities, propulsion systems, communication protocols, these are routinely classified or released only under strict controls. But 3i Atlas is not a military satellite. It is an interstellar comet, a natural object, the kind of thing scientists live for. Why would governments care enough to intervene? The answer, if the extraordinary hypothesis is correct, lies in the implications. If the observations showed something inconsistent with natural formation, if the composition was anomalous, if the structure suggested design, then the question stops being a scientific curiosity and becomes a matter of profound national and global significance. How do you tell 7 billion people that we might not be alone, that something is visiting, that we have no idea what it wants or where it came from? How do you prevent panic, maintain social order, coordinate international response? You buy time. You impose temporary silence, you convene experts behind closed doors. You work through scenarios, you craft messages, you decide what to say and when to say it. And while all this happens, the public, kept in the dark, begins to sense that something is wrong, that the absence of information is itself information, that the silence is not empty but full of dread. The Mars vantage point matters immensely in this scenario. Observing 3i. Atlas from Earth provides one perspective, but observing it from Mars provides triangulation, depth perception, the ability to measure parallax and extract three-dimensional structure. If the object displayed geometry inconsistent with a tumbling ice ball, if it showed bilateral symmetry or surface features that looked machined, if it exhibited maneuvers or changes in brightness that suggested active control, then the view from Mars would be the smoking gun, the data point that transforms speculation into conclusion. And that brings us to the question lurking beneath every layer of this mystery. What would such data actually show? What would an artificial interstellar object look like? Would it be obviously technological, bristling with antennas and solar panels like a spacecraft from a science fiction film? Or would it be subtle, optimized for interstellar travel in ways we cannot yet imagine, its purpose and origin ambiguous even to trained observers? Would we recognize it for what it is? Or would we argue about it, split into camps, fight over interpretation, while the object continued on its hyperbolic path toward the outer solar system and oblivion? The chemistry results, which we will explore in depth shortly, add fuel to this fire. Initial spectroscopic observations suggested unusual composition, particularly in excess of carbon dioxide relative to water vapour and hints of nickel without corresponding iron, both of which are atypical for known comets. If the Mars observations confirmed or extended these anomalies, if they added morphological strangeness to chemical strangeness, then the case for something extraordinary becomes harder to dismiss with hand-waving about data artifacts and processing errors. We are left in limbo, suspended between the mundane and the extraordinary, unable to move forward without the data that should have been released weeks ago. Behind closed doors, if the extraordinary hypothesis is correct, people with access to that data are having conversations we can only imagine. Scientists presenting results, officials asking questions, risk assessors modelling scenarios, communication strategists drafting statements. And outside those closed doors, the rest of us wait, watching the silence, interpreting its texture, its weight, its implications. The vacuum will not last forever. Data, like water, finds a way to leak. Someone will talk. Something will slip. The information environment cannot be controlled indefinitely, not in an age of social media and citizen journalism and hackers and whistleblowers. Eventually we will know what those instruments saw when they pointed at 3i Atlas as it passed Mars. The only question is whether we will learn it through official channels, carefully framed and contextualized, or through leaks and rumours and fragmented disclosures that create more confusion than clarity. Until then, we have only the silence, the smudge, and the growing certainty that something is happening behind doors we cannot open. Part 6. The data that never dropped. The Planetary Data System is NASA's official archive, a sprawling digital repository where spacecraft observations are supposed to live forever, publicly accessible, free to anyone with an internet connection, and the patience to navigate its labyrinthine structure. The European Space Agency maintains a similar resource called the Planetary Science Archive, a parallel universe of images and spectra and telemetry, from European missions to Mars, Venus, comets and moons throughout the solar system. These archives are not optional extras, nice-to-have features that agencies maintain when convenient. They are mission requirements, encoded in funding agreements, mandated by policy, the price of doing science with public money. Transparency is the deal. We give you billions of dollars to launch robots into space, and you give us the data, all of it, calibrated and documented and free. So where, in these vast digital warehouses, are the 3i Atlas observations from the Mars flyby window? Let us walk through the search, carefully and methodically, to understand what exists and what is conspicuously absent. Start with the Planetary Data System, specifically the sections dedicated to Mars missions. Navigate to Mars Reconnaissance Orbiter to high-rise image releases. Filter by date, October 1st through October 7th, 2025. Apply search terms. 3i Atlas, InterstellarObject, Visitor. The results are sparse, almost mocking in their emptiness. no dedicated image sets, no observation logs tagged with the object's name, no press releases linked to data deposits. Try Mars Express through the European Planetary Science Archive. The interface is different. The organisation follows European conventions, but the principle is the same. Query the database for observations during the target window. Look for spectroscopic data, camera images, pointing logs that would indicate the spacecraft turned its instruments toward the expected position of 3i Atlas. Again, nothing. Or rather, nothing obviously tagged and readily accessible. Perhaps the data is there but mislabeled, buried under generic mission identifiers, waiting for someone with the right keywords and persistence to extract it. But if that is the case, it represents a failure of data management so profound that it might as well be deliberate. The European Space Agency's public statement, made before the flyby, explicitly said Mars Express and the Trace Gas Orbiter would observe 3i Atlas between October 1st and 7th. This was not a vague intention or a hopeful plan. This was an announced observation campaign, the kind of commitment that normally results in press releases, blog posts, image galleries, and data uploads. The absence of follow-through is jarring. Agencies announce campaigns to build public interest, to justify budgets, to demonstrate mission value, when those campaigns then vanish without explanation or result. Questions multiply. Community sleuths on X, the platform formerly known as Twitter, have been cross-referencing timestamps, checking observation schedules, comparing data upload patterns before and after the flyby. Their findings, compiled in long threads and shared documents, paint a picture of a data gap. Normal mission operations continued, images of the Martian surface kept appearing, routine science kept happening. But the 3i Atlas window appears sanitized, as if someone scrubbed the archives of anything related to the interstellar visitor. Now, before we descend into conspiracy theory, let us consider the benign explanations again, because intellectual honesty demands it. Perhaps the pointing was not as precise as planned. Mars orbiters are designed primarily for observing Mars, not for tracking fast-moving objects against the star background. Attitude control systems optimized for nadir pointing straight down at the planet might struggle with off-axis targets that require rapid slews and precise tracking. Perhaps the observation attempts failed technically, and agencies decided not to publicize failed observations because there was nothing interesting to report. Perhaps the signal-to-noise ratio was simply too low. 3i Atlas, while bright enough for Hubble to image from Earth orbit, might have been much dimmer when viewed from Mars, especially if the coma structure was not favourably oriented toward the observers. Perhaps scattered light from Mars itself, sunlight bouncing off the atmosphere and surface, created background noise that drowned out the faint signal from the comet. These are the kinds of practical challenges that plague observational astronomy. The difference between theory and reality, between what you hope to capture and what the physics actually allows. Perhaps calibration proved more difficult than expected. Raw images from spacecraft often contain artifacts, hot pixels, readout noise, compression artifacts, geometric distortions from lens optics or sensor characteristics. Removing these requires careful processing, comparing observations against calibration targets, applying correction algorithms that can take days or weeks to run. Perhaps the teams responsible for this work are understaffed, overworked, dealing with backlogs from other high-priority observations. Perhaps the 3i Atlas data is sitting in a queue somewhere, waiting its turn, no conspiracy required, just the mundane friction of large organisations with limited resources. There is also the possibility of legal or political review, not because the data shows anything extraordinary, but simply because multiple nations and agencies were involved. Coordinating publication across international partnerships can be bureaucratically nightmarish. Who gets to publish first? Who gets credit? What language appears in the press release? These questions, petty as they seem, can delay data, release for weeks while lawyers and administrators negotiate. Science is collaborative, but scientists and their institutions still compete for recognition, funding, and priority. The spicier explanations, clearly labelled as speculative, involve deliberate information control. Perhaps an interagency request was made to hold imagery temporarily. Perhaps the request came from intelligence communities concerned about operational security, worried that detailed images of tracking a fast-moving object might reveal satellite capabilities or sensor technologies that are classified for national security reasons. Perhaps the request came from diplomatic channels, an attempt to coordinate messaging around a discovery that all parties agreed was significant enough to require careful handling. Perhaps, and this is the darkest speculation, defense sensors saw something the civilian instruments missed or confirmed, and a decision was made at a level above the space agencies to pause publication pending analysis. The United States, Russia, China, and other spacefaring nations maintain extensive space surveillance networks designed to track satellites, debris, and potential threats. These networks are far more sensitive and capable than civilian telescopes, though their existence and capabilities are often classified. If such sensors detected anomalous behavior from 3i Atlas, if they saw course corrections or brightness changes or structural details that suggested something other than a natural comet, then civilian agencies might be asked to hold data while experts evaluated the implications. These scenarios are not proven. They are not even particularly likely, but they are possible, and in the absence of official explanation for the data gap, they fill the void that silence creates. The human mind demands narrative. When facts are scarce, speculation flourishes. The longer the agencies wait to explain themselves, the more elaborate and paranoid the alternative explanations become. It is worth noting that NASA and Hubble did publish information about 3i Atlas earlier in the year. Size estimates, orbit calculations, compositional data from spectroscopy all appeared in official channels and peer-reviewed papers. The agencies have not been completely silent about the object. What is specifically missing is imagery and data from the Mars flyby window, that narrow period when multiple spacecraft with unprecedented vantage points should have been capturing their best observations. The selectivity of the silence is what makes it so provocative. Archives can be searched, logs can be checked, patterns can be analysed. But if data was never uploaded, or if it was uploaded under obscure identifiers that do not reference 3i Atlas, then even the most diligent citizen scientist will come up empty. The architecture of these archives assumes good faith, assumes that mission teams want their data to be found and used. If that assumption breaks down, if data is effectively hidden in plain sight through mislabeling or omission, then the public's right to access becomes theoretical rather than practical. We are left with an uncomfortable asymmetry. The infrastructure exists for transparency, the policies demand it, the precedents support it. But the data from the most anticipated observation campaign of the year, involving billions of dollars of hardware and explicit public announcements of intent, is absent from the places it should be. Whether that absence reflects technical failure, bureaucratic dysfunction, or deliberate choice, we cannot yet determine. But the absence itself is a fact, verifiable and troubling, and it sits at the centre of everything strange about the 3i Atlas story. The data that never dropped has become the data that everyone is talking about, and its very invisibility has given it more power than any image could have achieved. Part 7. When smudge becomes structure. Let us return to the image that will not go away, the elongated glow that has become the visual shorthand for this entire mystery. Pull up the processed Perseverance frames again, the stacked images that show 3i Atlas as a streak of light against the Martian sky. Zoom in on the versions that have been contrast enhanced, the crops where the object appears cylindrical, almost uniform in brightness along its length, with what some observers describe as crisp edges and internal structure. Look at the false colour versions, the ones tinted green or enhanced to bring out subtle details. Does this look natural? Does this look like a tumbling comet nucleus surrounded by a diffuse coma of gas and dust? Or does it look like something else? Something organised? Something that does not belong in our comfortable categories? The human eye is a miracle of evolution and an engine of deception. We see faces in clouds, animals in rock formations, patterns in randomness. Pareidolia, the tendency to perceive meaningful images in ambiguous stimuli, is hardwired into our neural architecture. It kept our ancestors alive, helped them spot camouflaged predators and hidden food sources, but it also makes us unreliable interpreters of noisy data. A smudge becomes a cylinder, a trick of light becomes evidence, an artifact becomes an artifact in the archaeological sense, proof of intention and design. So let us approach this carefully, with the skepticism it deserves, but also with the openness that science requires. Start with motion blur, the most prosaic explanation. When a camera captures a moving point source, especially across multiple frames that are later aligned and stacked, the motion creates elongation. The direction of elongation should match the direction of motion. The length should correspond to the angular velocity multiplied by exposure, time multiplied by the number of stacked frames. This is basic kinematics, predictable and testable. If the cylinder shape can be fully explained by these factors, then there is no mystery, only misinterpretation. But some analysts claim the internal brightness distribution is too uniform for simple motion blur. When a point source streaks across a detector, the resulting trail typically shows brightness variations, brighter in the center where the photons concentrated, fainter at the edges where fewer photons were collected. The stacked images, according to these analysts, show almost constant brightness along the length of the object, suggesting not a smeared point, but an extended source with intrinsic structure. They point to what they interpret as clean edges, boundaries that appear too sharp to be the diffuse coma of a comet. Then there is the controversial claim of a metallic band or gleam, visible in certain processing versions, a reflection or emission feature that looks distinctly artificial. This is where the analysis becomes most contentious, where skeptics and believers part ways completely. One camp sees obvious processing artifacts, hot pixels amplified by contrast enhancement, colour mapping creating the illusion of structure where none exists. The other camp sees something worth investigating, a signal that cannot be dismissed without access to the original data and rigorous testing. How would we actually test this? The scientific method at its core is about reproducibility and prediction. If 3i Atlas truly has an elongated cylindrical structure, then multiple observations taken from different angles and at different times should show consistent geometry. The apparent length and width should vary predictably based on viewing angle, following the mathematics of perspective. If different instruments captured the object, their images should agree on basic morphology, after accounting for differences in resolution and wavelength sensitivity. Furthermore, if the elongation is purely due to motion blur in the Perseverance images, then we should be able to calculate the expected smear based on the known trajectory of 3i Atlas and the camera characteristics. If the observed elongation exceeds what motion blur can explain, or if the orientation does not match the predicted direction of motion, then the structure hypothesis gains credibility. These are straightforward calculations that require orbital mechanics and camera specifications, both of which are publicly available. But here is the problem. Without multiple independent observations, without images from the Mars orbiters that should have captured far superior data, we cannot perform these tests. We are stuck with ambiguous evidence, a single set of images from an instrument never designed for this purpose, processed by well-meaning amateurs using techniques that might introduce as many artifacts as they reveal. The cylinder could be real. The cylinder could be an illusion. We cannot tell the difference from this data alone. Avi Loeb's blog post acknowledging the stacked smudge lends some credibility to the observation, if only because Loeb is a professional astronomer affiliated with Harvard and the Smithsonian Astrophysical Observatory, not a conspiracy theorist or UFO enthusiast. Loeb has become controversial in recent years for his willingness to seriously consider the possibility of interstellar artifacts and extraterrestrial technology, but he remains a working scientist with publications in peer-reviewed journals and a reputation to protect. His interest in 3i Atlas does not prove the object is artificial, but it does validate the observation as worth examining rather than dismissing out of hand. The contrast with Hubble's July image is stark and instructive. That photograph, taken from Earth orbit months before the Mars flyby, shows a classic cometary appearance. The nucleus is small, perhaps a few kilometers across based on brightness and assumed albedo. The coma is symmetric, teardrop-shaped, exactly what sublimating ices should produce as solar radiation heats the surface and liberates gas and dust. The tail, if visible, would point away from the sun following the pressure of solar wind and radiation. Everything about the Hubble image screams comet, an icy relic from planetary formation, ejected from another star system and now passing through ours. So why does the Perseverance image look so different? Perhaps viewing angle explains it. Perhaps the geometry of the observation from Mars revealed structure that was hidden or blurred in the Earth-based view. Perhaps the object tumbles, and different observations captured different orientations. Perhaps, And this is where things get weird. The object changed between July and October, altering its appearance in ways that natural comets do not. The last possibility sounds like science fiction, but consider what it would actually require. Comets do change. Their activity waxes and wanes as different ice deposits are exposed to sunlight. Jets erupt from specific surface features, creating asymmetric comas and non-gravitational accelerations. Tumbling can alter brightness as different faces rotate into view. A comet observed in July might look quite different in October, purely through natural processes, but a change from symmetric coma to apparent cylindrical structure stretches the bounds of what known cometary physics can explain. We need more data. That sentence appears over and over in scientific discussions, a mantra of humility and frustration. The data exists. The Mars orbiters almost certainly captured images that would resolve these questions instantly. A single high-resolution photograph from HiRISE or Mars Express, properly calibrated and publicly released, would settle the structure debate completely. We would see either a comet nucleus with surrounding coma, or we would see something else, something that would require new explanations and uncomfortable questions. Instead, we have a smudge that half the internet interprets as a cylinder, and the other half dismisses as noise. The truth, maddeningly, remains locked in archives we cannot access, or was never captured because of technical failures we cannot verify. The geometry, the morphology, the reality of 3i Atlas as seen from Mars exists in a superposition of possibilities, neither confirmed nor ruled out, waiting for data release or whistleblower leak to collapse the wave function and show us what those instruments actually saw. Part 8. The nickel anomaly and the 10 to the 28th hypothesis. Chemistry does not lie, but it can whisper riddles that make astronomers lose sleep. The James Webb Space Telescope, humanity's newest and most powerful infrared observatory, turned its instruments toward 3i Atlas in the months before the Mars flyby. The near-infrared spectrograph, an instrument designed to split light into its component wavelengths and reveal the chemical fingerprints of distant objects, captured spectra from the comet's coma, that cloud of gas and dust surrounding the nucleus. What it found was unusual enough to warrant papers uploaded to Arxiv, the preprint server where astronomers share results before peer review, and unusual enough to spark conversations that blur the line between science and speculation. The dominant feature in the spectrum is carbon dioxide, far more abundant than water vapour. This is weird. Most comets we have studied, the ones that formed in our own solar system, are primarily water ice with carbon dioxide as a minor component. The ratio is typically reversed, water dominating, carbon dioxide present but secondary. 3i Atlas shows the opposite pattern, a carbon dioxide dominated coma that suggests either a very different formation environment or a very different composition from solar system comets. Keep it simple. Imagine a comet as a dirty snowball, a mixture of ices and rock and organic compounds left over from planetary formation. The exact recipe depends on where and when it formed. Closer to a star, water ice sublimates easily, so comets might be depleted in water and enriched in more volatile substances like carbon monoxide or carbon dioxide. Farther from a star, in the cold outer reaches of a planetary system, water ice is stable, and comets should be water-rich. The high carbon dioxide to water ratio in 3i Atlas suggests formation in a warm or unusual environment, or perhaps loss of water through previous close passes to stars on its journey through interstellar space. This is strange, but strange is not impossible. Comets are diverse. Every new one we study adds complexity to our understanding. 2I/Borisov, the previous interstellar comet, showed carbon monoxide abundances higher than typical solar system comets, a clue that planetary systems around other stars might have different chemical profiles. So carbon dioxide dominance, while unusual, is not by itself evidence of anything more than chemical diversity in the galaxy. Then come the nickel reports, and suddenly the conversation shifts from interesting to alarming. Multiple sources, including popular science outlets and blogs by astronomers analysing spectroscopic data, have claimed detection of nickel in the coma of 3i Atlas, but with little or no corresponding iron. This is the detail that makes chemists and astrophysicists sit up and pay attention, because it violates expectations based on how elements are manufactured in stars. Let us talk about stellar nucleosynthesis for a moment, the process by which stars forge elements heavier than hydrogen and helium. Small stars fuse hydrogen into helium. Larger stars continue the process, fusing helium into carbon and oxygen, then into neon, magnesium, silicon, all the way up the periodic table. The heaviest elements, including iron and nickel, are produced in supernova explosions, violent stellar deaths that scatter enriched material into space where it can be incorporated into new stars, planets, and comets. The key point: iron and nickel are produced together in supernovae, in predictable ratios determined by nuclear physics. When you find one, you expect to find the other. The cosmic abundance ratio of iron to nickel is well established, about 17:1 by mass. Comets, which formed from the same primordial material as everything else in a planetary system, should reflect this ratio, give or take some fractionation effects as different minerals condense at different temperatures. Nickel without iron, or with an extremely skewed nickel to iron ratio, is chemically bizarre. It suggests either a formation process that somehow separated these elements despite their similar properties, or it suggests contamination, or it suggests something that was never intended to mimic a natural comet in the first place. Some observers, including those affiliated with Harvard's Galileo project and the Initiative for Interstellar Studies, have pointed to this nickel anomaly as potential evidence of artificial composition, chemistry, that looks more industrial than astronomical. The 10 to the 28th hypothesis emerges from Bayesian reasoning applied to the probabilities. If you calculate the likelihood that a natural comet would have this specific combination of features, high carbon dioxide to water, nickel without iron, possibly cylindrical structure, and you compare it to the prior probability of artificial objects existing in interstellar space. Some analyses yield odds ratios favouring artificiality at levels like 10 to the 28:1. These are not peer-reviewed consensus values. These are speculative calculations that depend heavily on assumptions about priors and error bars, but they represent serious attempts by trained scientists to quantify how weird 3i Atlas actually is. Let us be clear about what these numbers mean and do not mean. A Bayesian odds ratio is only as good as the priors you feed it. If you start with a very low, prior probability for interstellar artifacts, say 1 in a billion, then even a high likelihood ratio from the data might not move the posterior probability above 1%. Conversely, if you allow for a higher prior probability, the same data could push your conclusion toward probably artificial. The calculation is mathematically rigorous, but the inputs are subjective, and garbage in means garbage out. Furthermore, the nickel without iron claim is contested. Some spectroscopists argue that iron lines are present but weak, or that detection thresholds make iron harder to see than nickel under certain conditions. There are alternative explanations involving selective outgassing, where certain compounds preferentially release nickel-bearing minerals while iron remains locked in refractory grains. There are concerns about line blending, where overlapping spectral features from different molecules create the illusion of nickel emission without corresponding iron absorption. The debate is technical, nuanced, and ongoing. What is not in dispute is that the chemistry of 3i Atlas is unusual. Even skeptics admit that. The question is whether unusual equals natural but rare, or whether unusual equals something else entirely. Chemistry, unlike images, is harder to misinterpret. Spectral lines correspond to specific atomic and molecular transitions. You cannot fake a nickel emission line any more than you can fake a fingerprint. If the detection is real, if the data is not corrupted or misidentified, then the nickel is there, and we need an explanation for why it is there without the iron we expect. The natural counters to the artificial hypothesis are important and should not be glossed over. Comets are compositionally heterogeneous. Different regions of the nucleus can have very different chemistry depending on where and how they formed. Outgassing is selective. Volatiles escape first, refractories last. The coma we observe is not a complete inventory of the nucleus, but a biased sample of whatever is actively sublimating at the time of observation. Detection thresholds matter. If iron is present but below the sensitivity limit of the instruments, while nickel happens to be in a more easily detectable state, we might see nickel without iron simply because we're not looking hard enough or in the right way. There is also the possibility of contamination, not in the sense of deliberate fabrication, but in the sense of foreground or background sources confusing the data. Spectroscopy from space telescopes is cleaner than ground-based observations, but it is not immune to scattered light, zodiacal dust, cosmic rays, and instrumental effects. Careful analysis requires subtracting these contributions, and mistakes can lead to spurious detections or missing features. The drama lies in the uncertainty. If the chemistry is as weird as the most provocative interpretations suggest, if 3I Atlas truly has a composition inconsistent with natural formation processes, then the implications cascade outward like a shockwave. We are not talking about life in the conventional sense, microbes on Enceladus or biosignatures in exoplanet atmospheres. We are talking about something that travelled between stars, something that might have been made rather than born, something whose existence would rewrite our understanding of our place in the universe. But we are not there yet. The data is ambiguous. The interpretations are contested. The peer review process has not reached consensus. What we have is a chemical puzzle wrapped in an information blackout, a mystery that could be solved with more observations, better spectra, independent confirmation, all of which should be forthcoming from the Mars observation campaign, but which remain frustratingly absent from the public record. The chemistry of 3I Atlas is strange enough to demand answers, but the agencies with the data to provide those answers have chosen, for reasons we can only guess, to remain silent. Part 9. A silent agreement among rivals. NASA and the European Space Agency compete for scientific prestige, for headlines, for the recognition that comes with discovery and the funding that follows recognition. China's space program competes even more directly, using each mission as a demonstration of technological and geopolitical strength, a signal to the world that the era of American space dominance is ending and a multipolar future is dawning. The United Arab Emirates, newer to the space arena, competes for legitimacy, for a seat at the table, for the respect that comes with contributing to humanity's collective knowledge. These agencies do not collaborate out of pure altruism. They collaborate when mutual benefit aligns interests, when shared costs make expensive missions feasible, when international treaties and diplomatic norms pressure them toward cooperation. But beneath the collaboration, the competition never stops. So when every major space agency with assets at Mars simultaneously goes quiet about 3I Atlas observations, when the normal rivalry for publication priority vanishes into a synchronized silence, observers notice. The coordination, if it is coordination and not coincidence, suggests communication channels operating above the level of individual missions, agreements made in conference rooms and phone calls we are not privy to, decisions influenced by considerations beyond pure science. Let us map the incentives clearly. NASA benefits from transparency. American taxpayers fund the agency, and public engagement justifies budgets. Publishing exciting results generates media coverage, inspires the next generation of scientists and engineers, maintains political support. The European Space Agency operates under similar pressures, with the added complexity of coordinating across member states, with different priorities and different levels of investment. Both agencies have decades of practice in managing public expectations, in explaining both triumphs and failures, in building trust through openness. China's incentives are different but equally strong. The China National Space Administration reports to a government that values control, but also craves international recognition. Publishing impressive results brings prestige. Demonstrating superior capabilities enhances national security by signalling technological strength to rivals. The silence around 3I Atlas in this context is a departure from established patterns that demands explanation. Either the data is not impressive, and Beijing chose not to publish mediocre results, or the data is too impressive, too sensitive, too fraught with implications that require careful handling. The European Space Agency's public announcement of observation plans complicates any conspiracy theory. They said, explicitly and openly, that Mars Express and the Trace Gas Orbiter would observe 3I Atlas between October 1st and 7th. That statement was made before the flyby, posted on official websites, repeated in media coverage. Transparency of this kind cuts against the idea of a premeditated cover-up. You do not announce observations you plan to hide, unless the situation changed, unless something unexpected appeared in the preliminary data, something significant enough that a subsequent request for embargo was made and agreed to. An embargo is not the same as classification. Classification involves legal authority, restricted access, potential criminal penalties for disclosure. An embargo is softer, a voluntary agreement among parties to pause publication pending further analysis or coordination. Scientific journals use embargoes routinely, giving reporters early access to papers on the condition that they not publish until an agreed date. This allows time for fact-checking, for interviews, for context, while ensuring that all outlets release simultaneously rather than competing for scoops. Could an embargo have been requested around 3i Atlas data? The mechanism would be informal, probably initiated through back-channel communications between space agency leadership and government officials. The justification might involve operational security, concern that detailed tracking data could reveal satellite capabilities, or it might involve diplomatic coordination, a recognition that discovery of something truly anomalous should be announced collectively rather than unilaterally, or it might involve scientific caution, a desire to verify unusual results before triggering public speculation. Historical precedents exist where science and state interests intersected in uncomfortable ways. During the Cold War, research with military applications was routinely classified. Even today, certain observations from space surveillance networks are not published because they reveal too much about sensor capabilities and orbital tracking methods. Data holds during sensitive, political events are not unheard of. The response to the Columbia Shuttle disaster involved careful sequencing of information release to avoid premature conclusions that might mislead families or the public. But 3i Atlas is not a military project, not a disaster, not a classified system. It is a comet, a natural object, the kind of phenomenon that belongs to all humanity. Why would any embargo apply? The speculative answer, unverified but logically coherent, is that someone's defense sensors saw something the civilian instruments either missed or could not definitively characterize. Space surveillance networks operated by the United States, Russia, and China are far more capable than anything accessible to civilian science. They track objects the size of softballs in low Earth orbit. They monitor geosynchronous satellites for anomalous behavior. They would absolutely notice an interstellar object passing Mars, and they might see details invisible to civilian telescopes. If those classified sensors detected structure, if they recorded maneuvers or brightness changes or emission spectra inconsistent with a natural comet, if military analysts concluded that 3i Atlas warranted further investigation before public disclosure, then civilian agencies might be asked to hold data temporarily. Not forever, not as part of a permanent cover-up, but just long enough for experts to assess the situation, for governments to coordinate their response, for communication strategies to be developed. This is speculation, clearly labelled as such, but it is not paranoid fantasy. Governments do coordinate around significant events. The discovery of gravitational waves, for example, involved months of internal verification before public announcement, though that was driven by scientific rigour rather than political sensitivity. The response to asteroid impact threats is coordinated through international bodies precisely because unilateral announcements could trigger panic or geopolitical tensions. A discovery suggesting extraterrestrial technology, even tentatively, even ambiguously, would warrant at least as much care. The irony is that coordination breeds suspicion. If all agencies had independently published their data on normal timelines, and the results were unexciting, no one would care. The collective silence, the synchronized absence of expected communication, creates the appearance of conspiracy whether or not conspiracy exists. The agencies have painted themselves into a corner. The longer they wait, the more suspicious the delay appears. The more suspicious it appears, the harder it becomes to explain away as routine operational issues. Meanwhile, online communities dissect every statement, every press release, every social media post from space agencies, looking for clues, inconsistencies, signs of coordination. The information war is not between believers and skeptics. It is between those who trust institutions and those who trust patterns, between those who default to boring explanations until proven otherwise, and those who default to something is being hidden until proven otherwise. The truth, if we ever learn it, will likely involve elements of both. Some of the silence is probably mundane, the result of failed observations, poor data quality, bureaucratic inertia. Some of it might be deliberate, a temporary pause while people who do not normally talk to each other have conversations about implications and options. Untangling which is which, without access to internal communications and decision-making processes, is nearly impossible. We are left reading tea leaves, interpreting shadows, building narratives from absence. What is certain is that the pattern of silence across agencies that normally compete is unusual, whether it reflects coordination or coincidence, intention or accident. We cannot yet say with confidence. But the question hangs in the digital air, unanswered and increasingly urgent. Who decided that the world should not see what Mars saw? Part 10. The Hidden War for the Narrative. The internet is not a single space, but a battlefield of competing realities, each armed with screenshots, citations, and absolute certainty. In one trench sit the debunkers, the skeptics, the people who have seen 1,000 viral mysteries evaporate under scrutiny and refuse to get excited until extraordinary claims meet extraordinary evidence. They look at the perseverance smudge and see motion blur, hot pixels, pareidolia. They point to the absence of corroborating data from other platforms as evidence that there is nothing to corroborate. They invoke Occam's razor, the principle that simpler explanations should be preferred over complex ones, and argue that pipeline delays plus noisy data plus human pattern. Recognition equals exactly the circus we are witnessing. No conspiracy required, no aliens necessary, just people seeing what they want to see in ambiguous images. In the opposite trench sit the anomalists, the people who look at the same data and see patterns too consistent to be coincidence, silence too coordinated to be accident, chemistry too weird to be natural. They catalogue the unusual features: high carbon dioxide to water ratio, possible nickel without iron, apparent cylindrical structure, simultaneous multi-agency blackout. They argue that each individual anomaly might have a mundane explanation, but the conjunction of all of them exceeds the threshold of reasonable doubt. They ask uncomfortable questions about why agencies that announced observation plans have not published results, about why the only publicly available images come from citizen scientists rather than official sources. The war between these camps is not fought with weapons, but with rhetoric, data interpretation, and social media algorithms that amplify outrage and certainty over nuance and doubt. Bot networks, whether state-sponsored or commercially, motivated, can amplify specific narratives, making fringe theories appear more popular than they actually are. Weibo moderation in China controls what space-related content reaches domestic audiences, shaping the information environment in ways that outsiders can only infer. The same event, viewed through different media ecosystems, can appear completely different. Facts cherry-picked and context-stripped until consensus becomes impossible. Yet this is not simply a matter of bad actors and manipulation. Genuine disagreement exists among people approaching the data in good faith. Astronomers with decades of experience analysing cometary spectra can reach different conclusions about the significance of compositional anomalies. Image processing experts can disagree about whether the Perseverance smudge shows real structure or artifacts. Risk analysts can calculate wildly different probabilities depending on their priors and assumptions. The scientific method is supposed to resolve these disputes through observation, experiment, replication. But when the crucial observations are locked away in archives we cannot access, the method stalls, and we are left arguing about shadows. For viewers trying to navigate this landscape, a toolkit is essential. First principle: anomalies should repeat. If 3i Atlas truly has unusual structure, future observations should confirm it. If the chemistry is genuinely weird, independent spectra from different instruments should agree. One data point, one ambiguous image, one contested measurement. These are insufficient to overturn our understanding of comets, or to claim discovery of artificial objects. Science requires reproducibility, consistency, accumulation of evidence. Second principle: demand transparency. Space agencies are publicly funded. The data belongs to all of us. When observations are announced and then never published, when archives that should contain images remain conspicuously empty, that is a failure of institutional responsibility regardless of what the actual data shows. Mundane explanations deserve mundane evidence. If the silence reflects routine pipeline issues, then agencies should say so explicitly, provide timelines for data release, restore public confidence through communication rather than radio silence. Third principle: distinguish between absence of evidence and evidence of absence. The lack of published images does not prove that something extraordinary was observed, but it also does not prove that nothing extraordinary was observed. We are in a state of uncertainty, a superposition where multiple explanations remain viable until collapsed by additional data. Premature certainty in either direction, absolute conviction that 3i Atlas is just a comet, or absolute conviction that it represents alien technology, is epistemologically unjustified. Fourth principle: hold the wow but remain curious. It is possible to be fascinated by this mystery without committing to a specific explanation. It is possible to demand better data without jumping to conclusions. It is possible to critique institutional silence without descending into paranoid conspiracy theories. Science at its best operates in this space of rigorous uncertainty, comfortable with not knowing, insistent on finding out. The hidden war for the narrative will continue until the data emerges, or the story fades into the background noise of internet controversies. But the war itself matters less than what it reveals about our relationship with institutions, with evidence, with the unknown. We live in an age where everyone has access to raw spacecraft data, but almost no one has the training to interpret it correctly. We live in an age where algorithms amplify division and reward outrage. We live in an age where the gap between what experts know and what the public understands has never been wider or more consequential. 3i Atlas, whatever it ultimately proves to be, has become a mirror reflecting our collective anxieties about control, about transparency, about whether the people in charge are telling us the truth or managing our perceptions. The object itself, speeding away from the sun on its hyperbolic trajectory, does not care about our debates. It does not care whether we interpret it correctly or miss it entirely. But we care because in asking what 3i Atlas is, we are really asking who we are, whether we are alone, and whether we can trust the institutions we have built to help us find answers. The narrative war is not over. New information will leak or be released. New analyses will be published. The cycle of claim and counterclaim will continue. But here, at this moment, suspended between discovery and explanation, we can be certain of one thing. Whatever is in those Mars observation archives exists. The data is real. The images, good or bad, clear or ambiguous, boring or extraordinary, are sitting on servers somewhere. And eventually, through official channels or unofficial leaks, we will see them. The question is whether we will be ready for what they show. Part 11. The Green Comets, Atlas, Lemon and Swan. While Mars goes quiet, the rest of the sky gets impossibly loud. 3 comets, 3 glowing green visitors, all visible in the same narrow window of time, have turned backyard astronomers into excited children and casual observers into amateur sky watchers. C/2025 K1 Atlas, not to be confused with our controversial interstellar visitor, brightens in the pre-dawn sky. C/2025 A6. Lemon follows its own trajectory, visible through binoculars or modest telescopes. C/2025 R2. Swan rounds out the trio, a late addition that brings the count to 3 simultaneous green comets, where typically we might see one or none. The internet, that great collective consciousness, marvels at the coincidence, shares photographs, asks whether this is normal or whether something strange is happening above our heads. Let us address the green immediately because colour in astronomy often misleads. The green glow comes from diatomic carbon, molecular C2, 2 carbon atoms bonded together, a molecule that forms in the coma as sunlight breaks apart more complex organic compounds. When ultraviolet light from the sun excites C2 molecules, they emit photons at specific wavelengths in the green part of the spectrum, around 510 and 515 nanometers. This is the same process that creates the auroras, though with different chemistry. The result is a green haze surrounding the nucleus, brightest near the centre, where outgassing is most intense, fading toward the edges where the coma dissipates into space. Green comets are not rare. Many comets appear green when they brighten, and outgassing becomes vigorous enough to produce detectable C2 emission. What is unusual is having 3 bright enough to notice simultaneously, creating a visual spectacle that invites pattern seeking and coincidence detection. Are they physically related? No. Do they share a common origin? No. Their orbits are completely different. Their discoveries span months. Their characteristics vary. They just happen to be in our neighbourhood at the same time, each following its own path, each brightening on its own schedule. But timing feels uncanny when you are primed for strangeness. The 3i Atlas controversy has sensitized people to anything unusual in the sky. A normal astronomical event, 3 moderately bright comets visible within weeks of each other, becomes suspicious by association. Social media threads compile the sightings, note the timing, draw connections that may not exist. 3 green comets at once and 3i Atlas goes silent. What are the odds? The odds, of course, depend on how you define the question. Comets follow no schedule. Their arrivals are random from our perspective, determined by orbital mechanics millions of years in the making. Still, the invitation to observe is real and valuable. These are accessible objects, not requiring professional equipment, visible from dark sky locations to anyone with patience and a star chart. C/2025 K1 Atlas reaches peak brightness in late October, visible before dawn in the eastern sky. C/2025 A6 Lemon follows a similar schedule, though slightly dimmer, requiring binoculars for most observers. C/2025 R2 Swan, the most recently discovered, adds a third point to the constellation of green visitors, each one a reminder that our solar system is not empty space, but a dynamic environment where objects constantly move, interact, evolve. For casual observers, the viewing instructions are straightforward. Find a location away from city lights, where light pollution does not drown faint objects. Check sky charts for current positions, which change nightly as comets move, against the background stars. Allow your eyes 20 minutes to adapt to darkness, a process that expands pupil size and shifts retinal chemistry toward maximum sensitivity. Look for a fuzzy patch, not a sharp point like a star, with possibly a faint tail extending away from the direction of the sun. Binoculars or a small telescope will reveal more detail, the green colour becoming apparent where naked eye sees only pale glow. Brightness in astronomy is measured on a magnitude scale that runs backward. Smaller numbers mean brighter objects. The sun is magnitude -27. The full moon is magnitude -13. The faintest stars visible to dark adapted eyes are around magnitude 6. Comets, being diffuse rather than point sources, appear dimmer than their total magnitude would suggest because their light is spread across an extended area. A magnitude 5 comet might be barely visible as a fuzzy patch, while a magnitude 5 star would be easily spotted. Understanding this helps manage expectations. These green comets are not spectacular naked eye objects dominating the sky. They are subtle, requiring effort and appropriate conditions, rewards for those willing to wake before dawn and drive away from urban glow. The emotional response to seeing a comet is difficult to articulate but unmistakable when experienced. There is the intellectual knowledge that this object has travelled from the outer solar system, perhaps from the Oort cloud trillions of miles away, following an orbit shaped by gravitational perturbations over millions of years. There is the visual beauty, the soft glow, the tail, if visible, stretching like a cosmic brushstroke across the stars. And there is the existential vertigo, the realization that you're standing on a planet orbiting a star watching another object that is also orbiting the same star, both of you moving through space at velocities that would be incomprehensible, except that everything is moving so we feel stationary. No known physical link connects these three comets to 3i Atlas. They are not escort vessels, not advanced scouts, not part of a coordinated arrival. They are solar system natives, icy bodies from our own cosmic neighbourhood, not interstellar visitors. The timing is coincidence, albeit a striking one that feeds the narrative hunger surrounding the larger mystery. But coincidences happen. In a universe vast enough and old enough, unlikely events become inevitable given sufficient opportunities. 3 moderately bright comets appearing simultaneously is improbable, but not impossible. Mundane when analysed, but eerie when experienced against the backdrop of unanswered questions about the interstellar visitor. What the trio does provide is context, a reminder that comets are numerous, varied, active. They are not rare exotic objects, but common features of planetary systems. Every star probably has a comet cloud, reservoirs of icy debris left over from planet formation, perturbed by passing, stars and galactic tides into orbits that occasionally bring them sunward. We live in a shooting gallery, a cosmic pinball machine where collisions and close passes shaped the early solar system, and continue to pose both opportunities for observation and risks for civilization. The green comets also democratize astronomy in a way that Mars observations do not. You cannot see 3i Atlas without professional equipment. You cannot verify the cylinder claims without access to spacecraft data. But you can step outside before dawn, look up, and see these 3 visitors with your own eyes or simple binoculars. The experience is unmediated, direct, personal. No institution controls it. No embargo can hide it. The sky is transparent in a way that space agency archives are not, and perhaps that transparency is what makes the institutional silence around 3i Atlas so jarring. We are accustomed to seeing what is there, to trusting our own observations. When those observations are replaced by controlled releases and unexplained delays, we feel a loss deeper than mere curiosity. So observe the green comets, enjoy them, share photographs, teach children to find them, celebrate the fact that the universe continues to put on shows regardless of what governments and agencies decide to reveal or conceal. And while you're out there in the pre-dawn darkness, staring up at green glows billions of miles away, remember that Earth itself is being watched, that our planet is not immune to the strange events unfolding in the larger solar system, that the cosmic theatre includes us whether we realise it or not. Part 12. Earth Trembles, Kamchatka's Fury. The ground does not stay still, not in Kamchatka, where the Pacific tectonic plate drives beneath the Eurasian plate in a process called subduction that has built one of the most volcanically active regions on Earth. Reports and live streams from the Russian Far East describe abnormal seismic activity, earthquakes clustering in patterns that seismologists note but cannot fully explain, volcanic ash plumes reaching altitudes that disrupt air traffic and paint sunsets in shades of orange and purple. Klyuchevskaya Sopka, the highest active volcano in Eurasia, at 4,750 metres, erupts with particular vigour. Shiveluch, another major volcano in the region, contributes its own ash and lava. The Ring of Fire, that horseshoe of tectonic boundaries encircling the Pacific Ocean, lives up to its name with intensity that feels, to observers primed for pattern recognition, suspiciously well-timed. Let us be clear about what we know versus what we imagine. Kamchatka is always active. Subduction zones generate continuous seismic activity as one plate grinds beneath another, friction creating earthquakes, melted rock rising through fractures to feed volcanoes. The region averages thousands of earthquakes per year, most too small to notice, some large enough to damage buildings and infrastructure. Volcanic eruptions occur regularly, some effusive and slow, others explosive and dangerous. This is normal geology, the ongoing process of planetary heat loss and crustal recycling that has shaped Earth for billions of years. What makes the current activity noteworthy, if it is noteworthy and not simply confirmation bias amplifying routine events, is the perceived clustering, the timing relative to other anomalies, the way seismometers and webcams have become narrative ammunition in the larger story about 3i Atlas and cosmic visitors. YouTube channels stream live footage from Kamchatka volcanoes, 24-hour feeds showing glowing lava, ash clouds, the raw power of Earth's interior breaking through the crust. Comment sections fill with speculation. Solar activity, gravitational perturbations, interplanetary dust, geomagnetic fluctuations, even direct causation by interstellar objects somehow triggering seismic events through mechanisms that violate known physics but satisfy narrative hunger. Could solar wind variations modulate Earth's ionosphere and atmosphere in ways that correlate with seismicity? The honest answer is that no established causal mechanism links space weather to earthquakes. Solar storms affect satellites, power grids, communication systems, auroras. They compress the magnetosphere, heat the upper atmosphere, drive currents in the ionosphere. But these effects occur hundreds of kilometres above the surface, far removed from the tectonic forces that generate earthquakes. The energy involved is also insufficient. A major earthquake releases energy equivalent to thousands of nuclear weapons. Solar wind, while carrying enormous total power spread across vast distances, delivers negligible energy per square metre at Earth's surface. Could interplanetary dust, perhaps associated with comets or interstellar visitors, somehow trigger volcanic activity? Again, no known mechanism supports this. Volcanoes erupt when magma pressure exceeds the strength of overlying rock, when gas bubbles nucleate and expand, when tectonic forces create pathways for molten material to reach the surface. These are internal processes driven by Earth's heat engine, independent of what happens in space beyond the atmosphere. But the human mind craves connection, especially when multiple unusual events occur within a compressed time frame. 3i Atlas passes Mars amid unexplained silence. 3 green comets appear in our skies. Kamchatka erupts with perceived increased intensity. An asteroid skims past Earth at altitudes lower than some satellites. Each event, considered individually, is mundane or at least explainable. Considered collectively, they form a narrative that feels significant, a pattern that demands interpretation even when no pattern may actually exist. This is the psychology of overlapping anomalies, the fuel that drives every conspiracy theory and every genuine discovery. The challenge is distinguishing between meaningful correlation and coincidental timing, between true patterns and pareidolia applied to events rather than images. Science offers tools for this: statistical analysis, mechanistic models, controlled experiments. But applying those tools requires data, access, transparency. When some of the events in question are subject to information control, when space agencies remain silent about observations they announced, when the baseline for normal becomes contested, the ability to separate signal from noise degrades. The Kamchatka activity matters to our story not because it is actually connected to 3i Atlas, but because it demonstrates how multiple unrelated phenomena can become narratively entangled when people are primed to see connections. It matters because it shows how live streaming and social media have changed the dynamics of information flow, making regional events globally visible in real time, inviting interpretation by audiences with no geological training or regional context. It matters because it reveals the appetite for escalation, the desire for stakes to increase, for the story to expand beyond a distant Mars to include our own planet, our own vulnerability. Earth trembles because Earth is geologically active, because plate tectonics have not stopped, because the planet is still cooling from its formation 4.5 billion years ago. The timing relative to other events is coincidence until proven otherwise. But coincidence feels inadequate when you're watching ash plumes rise into the atmosphere, when you're reading reports of evacuations and disrupted flights, when you're scrolling through YouTube comments claiming that something big is happening and they are not telling us everything. Perhaps the lesson is that living on an active planet in a dynamic solar system means accepting uncertainty, means recognizing that unusual events will occasionally cluster by pure chance, means resisting the temptation to weave every anomaly into a grand unified conspiracy. Or perhaps the lesson is that when institutions fail to communicate clearly, when silence replaces transparency, people will create their own explanations, will find their own patterns, will connect to dots that may or may not form a coherent picture. The truth, as always, lies somewhere in the tension between skepticism and openness, between demanding evidence and acknowledging ignorance. Part 13. The Webb Revelation, M87's jet. 55 million light-years away, an almost incomprehensibly violent process unfolds in the core of a giant elliptical galaxy called Messier 87. A supermassive black hole, 6.5 billion times the mass of our Sun, devours surrounding material while simultaneously launching a jet of particles and energy that stretches thousands of light-years into intergalactic space. The jet is straight, coherent, organised, powered by magnetic fields, twisted and amplified in the accretion disk swirling around the black hole's event horizon. The James Webb Space Telescope, with its infrared sensitivity and unprecedented resolution, has captured the clearest images yet of this cosmic phenomenon, revealing bright knots within the jet, shock fronts where particle acceleration creates brilliant emission, structure that looks designed even though we know it is natural. The imagery is stunning, genuinely breathtaking in a way that transcends technical appreciation and reaches for something aesthetic, almost spiritual. To see a jet extending across distances that dwarf entire star clusters, to recognise that this structure has been actively maintained for millions of years, to understand that the energy involved could power billions of civilizations, creates a visceral sense of the universe's capacity for grandeur. This is nature operating at scales and intensities that make human concerns feel trivially small. Why does this matter to our story about 3i Atlas? Because it provides crucial context for what looking artificial actually means. The jet from M87 looks engineered. It looks like a cosmic fire hose, a directed energy weapon, a transportation corridor, a megastructure. The straightness alone, maintained across thousands of light-years despite gravitational perturbations from stars and dark matter, seems to require fine-tuning and active control. The brightness variations along its length suggest machinery, components, purpose. But we know, through decades of theoretical work and observational confirmation that black hole jets are natural. They form from well-understood physics, conservation of angular momentum, magnetic field amplification through dynamo processes, particle acceleration in shock fronts, synchrotron radiation from relativistic electrons spiraling in magnetic fields. The equations are complex, the simulations require supercomputers, but the phenomenon emerges from basic principles without invoking intelligence or intention. Nature, given sufficient energy and the right boundary conditions, can create structure that rivals anything we could design. This is the humility that science demands and that speculation often forgets. When we see something that looks organized, that displays symmetry or coherence or apparent purpose, our first instinct is to invoke a creator, an engineer, an intelligence. But the universe is full of counterexamples, snowflakes with six-fold symmetry formed by simple crystal growth, spiral galaxies with elegant arms, shaped by density waves and differential rotation, planetary rings sorted by size through gravitational resonances. Complexity emerges from simplicity. Order arises from chaos. The appearance of design does not guarantee a designer. Apply this lesson to 3i Atlas. Even if the Perseverance images show cylindrical structure, even if the chemistry is unusual, even if the silence from space agencies suggests something significant, we must hold open the possibility that nature is simply being creative in ways we have not encountered before. Interstellar space is a different environment from the solar system. Objects that form around other stars experience different radiation fields, different chemical abundances, different gravitational histories. We have sampled 2 interstellar visitors before 3i Atlas, Oumuamua, which showed anomalous acceleration and triggered debates about whether it was a comet or something else, and 2i/Borisov, which looked more conventionally cometary, but still displayed compositional differences from solar system comets. Our sample size is tiny. Our understanding of what is possible is incomplete. The M87 jet also reminds us that energy and organisation are not synonymous with technology. A black hole jet carries more energy than all the starlight in its host galaxy. It maintains coherence across distances that would take light thousands of years to traverse. It shapes the intergalactic medium, heating gas, suppressing star formation, influencing the evolution of galaxy clusters. Yet it is mindless, purposeless, a consequence of gravity and magnetism and thermodynamics, nothing more and nothing less. This does not mean we should dismiss anomalies or refuse to consider extraordinary explanations. It means we should calibrate our expectations, recognize that looking designed is insufficient evidence for actual design, demand multiple independent lines of evidence before accepting claims that overturn conventional understanding. The M87 jet looked artificial before we understood it. Pulsars looked artificial when first discovered in 1967, regular radio pulses so precise that astronomers briefly considered the possibility of extraterrestrial beacons before realizing they were observing rotating neutron stars. Fast radio bursts looked artificial until we developed natural models involving magnetars and supernova remnants. The pattern is clear. Nature's toolbox is larger than our imagination. Every generation of astronomers encounters phenomena that stretch the bounds of the expected, that invite speculation about intelligence or technology, that ultimately yield to natural explanation once sufficient data accumulates and theoretical work catches up. This is not an argument that 3i Atlas must be natural. It is an argument that we should not jump to artificiality just because we cannot immediately explain what we see. The philosophical beat here is important. We live in a universe capable of creating black holes that swallow stars and launch jets spanning galaxies. We live in a universe where quantum mechanics governs the behaviour of particles and general relativity warps space-time around massive objects. We live in a universe where complexity emerges at every scale, from subatomic to cosmic, through processes that require no guiding hand beyond the laws of physics. To invoke, design prematurely to claim artificiality before exhausting natural possibilities is to underestimate the creative power of those laws. Yet we must also remain open. If evidence genuinely points toward artificiality, if natural explanations fail repeatedly, and the artificial hypothesis makes testable predictions that prove correct, then we should follow the data wherever it leads. Science is not about protecting comfortable beliefs. It is about updating our models when reality demands it. The M87 jet teaches us caution. but it should not teach us closed-mindedness. For now, as we wait for the Mars observation data that could settle questions about 3i Atlas, the jet reminds us that the universe is full of wonders we barely understand, phenomena that challenge our intuitions and expand our sense of what is possible. Whether 3i Atlas joins the list of natural wonders, or whether it represents something genuinely unprecedented, the cosmos remains stranger and more magnificent than we generally allow ourselves to imagine. Part 14. Enceladus, the life beneath the ice. While Mars stays silent about its interstellar visitor, Saturn's moon Enceladus screams about something potentially more profound. The chemistry of life, active and accessible, erupting through cracks in an ice shell covering a global ocean. New analyses published this week in Nature Astronomy describe freshly ejected ice grains captured by spacecraft instrumentation during flybys years ago, but only now fully processed and understood. The grains contain complex organic molecules, not just simple carbon compounds, but larger structures involving nitrogen, oxygen, multiple carbon atoms bonded in ways that suggest chemical sophistication. These are the building blocks of amino acids, the precursors to proteins, the molecular machinery that life as we know it requires. Keep this accessible. Enceladus is tiny, barely 500 kilometers in diameter, small enough to fit inside the borders of Texas with room to spare. Its surface is frozen water ice, reflective and bright, keeping temperatures at negative 200 degrees Celsius. But beneath that ice, heated by tidal forces as Saturn's gravity flexes the moon's interior, lies an ocean of liquid water. We know this ocean exists because we see its contents erupting through fractures at the South Pole, geysers of water vapor and ice particles shooting hundreds of kilometers into space, some escaping Enceladus entirely to form one of Saturn's diffuse rings. The Cassini spacecraft, which orbited Saturn from 2004 until its deliberate destruction in 2017, flew through these plumes multiple times, using mass spectrometers to analyze the chemical composition of rejected material. The data showed water, obviously, but also salts, silica dust, hydrogen gas, and organic molecules. Each discovery strengthened the case that Enceladus harbors a habitable environment, a place where water, energy, and chemistry combine in ways that could support life. The latest analyses focus on the complex organics, molecules too large and structured to be simple contaminants, or random products of ice irradiation. Spectroscopic signatures match compounds found in some meteorites, the carbonaceous chondrites that carry organic material from the early solar system. But the Enceladus organics are fresh, recently produced or recently exposed, not ancient relics but active chemistry happening now. The implication is that the ocean beneath the ice is not just liquid water, but a chemical reactor, perhaps with hydrothermal vents on the seafloor, where hot mineral-rich water meets cold ocean, creating chemical gradients that life could exploit. This is not detection of life. No metabolism has been measured, no cells have been observed, no DNA or equivalent information carrying molecule has been identified. What we have is evidence of habitability, of an environment where life could exist if it arose or was introduced. On Earth, wherever we find liquid water with energy sources and chemical diversity, we find life. Deep ocean vents, Antarctic lakes beneath ice sheets, acidic hot springs, hypersaline lagoons, even rocks miles underground, all host microbial communities. Life is tenacious, adaptable, capable of exploiting niches that seem impossibly hostile to our surface-dwelling intuitions. Could Enceladus host life? The answer is yes, it could. The chemistry is promising. The energy budget, powered by tidal heating rather than sunlight, is sufficient. The timescales are favourable. The ocean has probably existed for billions of years, long enough for biology to emerge if the conditions permit. Whether life actually exists there remains unknown, unknowable without direct sampling, without missions designed to drill through the ice, or analyse plume material with instruments more sophisticated than Cassini carried. The narrative irony is delicious and frustrating. Space agencies openly discuss life-friendly chemistry at Saturn, publish papers in prestigious journals, hold press conferences celebrating the discovery of complex organics. The messaging is clear. Enceladus is a target, a place we should explore, a potential harbour for the second origin of life that would revolutionise biology and philosophy. Meanwhile, Those same agencies remain silent about imagery from Mars during the 3i Atlas flyby, silent about observations they explicitly announced, silent in ways that invite suspicion and speculation. Why the differential transparency? Perhaps because Enceladus, however exciting scientifically, poses no immediate existential questions. If we discover microbial life in the Enceladus ocean, it will be extraordinary, career-defining, headline-generating science. It will tell us that life arises wherever conditions allow, that the universe may be teeming with biology, that we are not unique. But it will be life we can study, life that does not challenge our technological primacy, life that exists on a scale and at a distance that makes it fascinating but not threatening. An interstellar visitor displaying artificial characteristics would be different. It would not be life we discovered through patient exploration. It would be technology that found us, that passed through our solar system, that demonstrated capabilities we cannot match. The implications would cascade beyond science into geopolitics, defense, religion, every domain where humanity's self-conception matters. The discovery would not belong to scientists alone. It would belong to everyone, ready or not, with no time for preparation or consensus building. So agencies talk about Enceladus and stay silent about 3i Atlas, not because one is more important than the other, but because one fits comfortably within existing frameworks, and the other threatens to break those frameworks entirely. This is speculation, admittedly, but it is speculation that fits the available facts better than any alternative explanation currently on offer. The Enceladus news also serves as a reminder that our solar system is not dead, not a collection of cold rocks orbiting a star. It is dynamic, chemically active, full of environments we barely understand. Europa, another moon with a subsurface ocean, shows similar promise. Titan, Saturn's largest moon, has lakes of liquid methane and organic chemistry so complex that some scientists call it a natural laboratory for prebiotic chemistry. Mars itself may have habitable environments in deep aquifers or ice deposits, places where microbes could persist despite the harsh surface conditions. We live in a system rich with possibility, and we have barely begun to explore it. The fact that agencies can be simultaneously transparent about some discoveries and opaque about others suggests a decision-making calculus we are not privy to, a sorting of information into categories labelled safe to release, and requires further consideration. Understanding that calculus, reverse engineering the criteria that determine which discoveries get press releases and which get silence, is as important as understanding the discoveries themselves. For now, celebrate the Enceladus findings. They represent science done right. Careful analysis, peer review, open publication, clear communication of what is known and what remains uncertain. Hold them as a standard against which to judge the 3i Atlas situation. Demand the same transparency, the same rigour, the same commitment to public knowledge. And remember that if life can emerge in the ocean of a tiny frozen moon, heated by tidal forces, if chemistry can become biology in environments we barely imagined habitable a generation ago, then the universe is far stranger and more fecund than we typically allow ourselves to believe. Part 15. The 250-mile mystery. On a Tuesday afternoon, most of Earth's population went about their day completely unaware that a space rock roughly the size of a small house skimmed past the planet at an altitude of approximately 250 miles, or 400 kilometres, placing it firmly within the altitude range where the International Space Station orbits, and where many satellites operate. Asteroid 2025 TF, designated with the bureaucratic efficiency typical of astronomical nomenclature, was spotted hours after its closest approach, detected by survey telescopes designed to catch exactly these kinds of objects, but not always in time to provide advance warning. The numbers are sobering. 400 kilometres is nothing in cosmic terms, barely a rounding error, the altitude where space shuttles once flew and where some commercial satellites conduct their business. This was not a distant flyby observed from millions of miles away. This was a close call, an object that could have intersected Earth's atmosphere if its trajectory had been slightly different, that could have delivered energy equivalent to multiple atomic bombs if it had struck populated areas. The shock is not that the asteroid passed safely. The shock is that we almost did not notice. Size matters here. Asteroid 2025 TF is small, perhaps 10 to 20 metres across depending on its composition and albedo. Objects this size are difficult to spot, especially when approaching from directions that place them against the daytime sky or near the sun where ground-based telescopes cannot easily observe. Our survey systems are improving, catalogues growing, detection rates increasing. But gaps remain, blind spots where objects can slip through unnoticed until they are already past us, or, worse, until they are already entering the atmosphere. Consider the Chelyabinsk meteor from 2013, a 20-metre object that exploded over Russia with energy equivalent to about 400 kilotons of TNT, shattering windows across a city, injuring over 1,000 people, stunning the world with dashboard camera footage of a fireball brighter than the sun. We did not see it coming. No warning was issued. The first indication most people had was the brilliant flash and the shockwave that followed minutes later. Asteroid 2025 TF could have been another Chelyabinsk, another surprise, another reminder that living on a planet in a solar system means sharing space with debris. Some of it harmless, some of it potentially catastrophic. The reason we miss objects like this is straightforward. Small size, high speed, unfavourable geometry. Detection requires reflecting sunlight back toward our telescopes, which means objects approaching from sunward directions are essentially invisible until they pass and can be observed against the dark sky. Phase angle, the angle between the sun, the object and the observer, dramatically affects apparent brightness. An asteroid can be thousands of times fainter when approaching than when receding, purely due to illumination geometry. Speed compounds the problem. These objects move fast, kilometers per second, crossing the field of view of a telescope in seconds or minutes, requiring automated detection systems that can distinguish moving objects from stars and noise. Survey programs like the Catalina Sky Survey, Pan-STARRS, and the upcoming Vera Rubin Observatory are working to solve this problem, scanning the sky repeatedly, building catalogues of known asteroids, calculating orbits to predict future close approaches. Progress is real. The number of known near-Earth asteroids has grown from hundreds in the 1990s to tens of thousands today. But completeness remains elusive. We have probably found most of the kilometre-sized objects, the ones that could cause global catastrophes. We have found many of the 100-metre objects, the ones that could destroy cities, but the 10 to 50-metre objects, the ones that could level neighbourhoods or create regional disasters, remain poorly catalogued. Asteroid 2025 TF fits into the nightmare scenario. Large enough to cause significant damage, small enough to evade detection until too late. If we can miss something that passes within 400 kilometres, if we can be surprised by an object that came closer than many satellites, then what else might we be missing? The question is not rhetorical. It is practical, urgent, a matter of planetary defence that requires resources, coordination, international cooperation. Connect this to 3i Atlas and the larger narrative thread. If we can miss an asteroid that passes within the orbit of our spacecraft, imagine what we could miss about an interstellar visitor that we only observed briefly from Earth and then lost in the glare of Mars and the Sun. If our surveillance gaps allow objects to slip past unnoticed, how confident can we be that we understand 3i Atlas based on limited observations and contested data? The surveillance problem is not just about asteroids. It is about everything that moves through our cosmic neighbourhood, natural or otherwise. The surveillance networks that track space objects are better than public systems, more sensitive, more comprehensive. The United States Space Force, successor to Air Force Space Command, monitors tens of thousands of objects in Earth orbit and beyond. Russia, China, and other spacefaring nations maintain similar capabilities. These networks can track objects much smaller than Asteroid 2025 TF, when those objects are in predictable orbits around Earth. But interstellar visitors, arriving from random directions at high velocities, are harder targets. They do not follow the predictable patterns of Earth satellites. They appear, pass through, disappear, often before we can fully characterize them. This is the context for the 3i Atlas mystery. We are partially blind. Our tools are powerful but limited. Our coverage is improving but incomplete. Our ability to characterize fast-moving objects depends on having multiple observations from different perspectives, exactly the kind of data that the Mars flyby should have provided, but which remains absent from public record. If Asteroid 2025 TF can sneak past our defences at 400 kilometres, what might 3i Atlas be hiding in plain sight simply because we lack the data to see it clearly? The wider point transcends any individual object. Surveillance gaps plus communication lags equals fertile ground for rumour, fear, and misinformation. When institutions fail to provide timely information, when objects surprise us, when we learn about close approaches after the fact, trust erodes. People begin to wonder what else is not being disclosed, what other near misses or actual hits might have occurred without public knowledge, whether the agencies responsible for monitoring cosmic threats are competent and transparent, or whether they are overwhelmed and secretive. Asteroid 2025 TF will fade from headlines within days, a footnote in the catalogue of near-Earth objects, a data point in statistical models of impact risk. But it should serve as a wake-up call, a reminder that we live in a shooting gallery, that space is not empty, that the gaps in our knowledge are larger than most people realise. And when those gaps intersect with mysteries like 3I Atlas, when surveillance failures compound communication failures, the result is exactly what we see now. A public hungry for answers, institutions reluctant to provide them, and a narrative that writes itself in the vacuum between question and response. Closing. The storyteller's silence. Pull back now, widen the frame, see the whole picture assembled from fragments and silences and unanswered questions. Your screen displays the montage, the cylindrical smudge from Perseverance, elongated and ambiguous, glowing against the Martian sky. 3 green comets scattered across Earth's pre-dawn darkness, separate but visually linked by timing and colour. The M87 jet in the background, a cosmic fire hose stretching across a galaxy 55 million light-years away, reminding us that nature builds structures that dwarf our imagination. Enceladus, tiny and frozen, harbouring an ocean that might cradle life. Kamchatka, erupting in orange and grey, Earth's own fury on display. And somewhere in the data, in archives we cannot access, the truth about what 3I Atlas looked like when multiple spacecraft observed it from Mars. Every light in the sky tells a story. The comets tell stories of ice and carbon and deep time, of objects formed billions of years ago finally perturbed into orbits that bring them sunward. The asteroid that skimmed past Earth at satellite altitude tells a story of near misses and surveillance gaps, of a cosmos indifferent to our presence. Enceladus tells a story of hidden oceans and complex chemistry, of possibilities we're only beginning to explore. The M87 jet tells a story of energy and gravity, and the universe's capacity for grandeur without intention. And 3I Atlas? Its story remains unfinished, suspended between observation and revelation, between data collected and data released. The storytellers, the space agencies with their instruments and archives, have chosen silence. Whether that silence reflects caution, coordination, bureaucratic inertia, or something more deliberate we cannot yet say. But the absence of their voices has created space for other voices, other narratives, other interpretations to flourish. The question hanging over everything is not what 3I Atlas is. The question is who decides when we learn the answer, and why those decision-makers believe silence serves better than transparency. Science thrives on openness, on the free exchange of data, on the ability of independent researchers to verify, challenge, extend each other's work. When that openness breaks down, when observations are announced but data never appears, when institutions that normally compete for credit suddenly align in their refusal to publish, we are left with the uncomfortable realization that the machinery of discovery is also machinery of control. Perhaps the Mars images show exactly what we expect. A comet, fuzzy and unremarkable, interesting scientifically but not paradigm-shattering. Perhaps the silence reflects nothing more than the grinding friction of large bureaucracies, the mundane reality that data takes time to validate and release. Perhaps in 6 months or a year, archives will fill with images, papers will appear, and we will look back on this moment as an exercise in premature speculation, a cautionary tale about reading too much into routine delays. Or perhaps something else is happening behind doors we cannot open, in conversations we cannot hear, among people with access to information we do not possess. Perhaps the images show structure that does not fit comfortable categories. Perhaps the chemistry is stranger than early reports suggested. Perhaps defense sensors saw something civilian instruments could not definitively characterize. Perhaps a decision was made, quietly and collectively, that this discovery requires careful handling, coordination, preparation before disclosure. We do not know, That is the honest answer, the scientifically rigorous position, the statement that encompasses both possibilities without committing prematurely to either. We do not know because the people who do know have not told us. And the longer they wait, the louder the silence becomes, the more elaborate the alternative explanations grow, the harder it will be to restore trust even if the eventual revelation is completely mundane. What we can say with certainty is that 3I Atlas passed Mars on October 3rd, 2025. Multiple spacecraft observed it, or attempted to observe it. Data was collected, transmitted, stored. Scientists have analysed that data. Reports have been written. Conclusions have been reached. All of this has happened. The information exists. It sits on servers, in databases, in classified or proprietary archives, waiting for release or leak or the slow passage of time to declassify it. The object itself, indifferent to our debates and desperate for answers, continues on its hyperbolic path outward from the Sun. It will pass beyond Neptune's orbit, beyond the Kuiper Belt, back into interstellar space, never to return. Future observations will become increasingly difficult as it fades into the darkness between stars. If we missed our chance to understand it, if the Mars flyby represented a unique opportunity now squandered by silence or secrecy, we may never get another. The window is closing, the moment is passing, and still the agencies say nothing. Every light in the sky tells a story, but some stories are told and others are kept, and the difference between the two reveals more about the storytellers than about the sky itself. We are left to wonder, to speculate, to demand answers that may or may not come. We are left to watch the silence, to interpret its texture, to ask why those with the power to illuminate choose darkness instead.